Assalamualaikum and good day. Today I would like to present a PID control based tuning method performance in electropneumatic ballast tank system or remotely operated underwater trawler. So this is presentation outline, consists of introductions, system details, which is we have system identifications, control strategy, electropneumatic schematic design, results and discussion, and last is conclusions. So for this purpose, we actually aim the tuning methods apply to PID control so that we can enable variable ballast systems of the ROUC or so-called remotely operated underwater trawler. And we want to ensure the underwater vehicles hydroplane when the altitude keeping over a variable seabed. So for this ROUC, which is used on the cut and pick the specimen, so normally apply in biodiversity research works. For this, our case study is on the seabed. Okay, so as we know, on the seabed we have a lot of obstacles. So this ROC need a very good conditions in terms of hydroplanes. So we need a electropneumatic ballast tank system. So that which is ROC need to keep stable during cutting and picking operations. So this is system detail. So we have MATLAB simulating control strategy algorithm. So we use this to develop a control strategy algorithm, which is PID control. So the controller that we use is PLC, Arduino based PLC. So we download all the algorithm inside this controller, so we can control all the 3-way solenoid valve in the electropneumatic ballast tank system of ROUC. So this is the input and output signal which is applied to the ROUC. So we need this data in order to have the model of the system. So we use a system identification apps of MATLAB. The model, which can be accepted due to the best fit percentage, is more than 90%. So for this case study, we have a validation curve. So it's measured from input and output, so that we can say that this is what we call the best fit for this output simulated based on the measured and simulated. Okay, we have 99.09%. So it means it's acceptable to use this validation curve for system identification model. So this is the system identifications discrete polynomial equations. You can see from equation 1, 2, and 3. From the results on the system identification apps, we receive final prediction error around 2.869 exponential power of negative 31, and the mean square error MSE is 2.25 negative 31. So the transfer function of ARX model, autoregressive model, can be obtained as you can see in equation 4. And the final transfer function we receive as in equation 5. So on this control strategy, we use the 3 methods of tuning. Okay, tuning methods involve is robust response time, Ziegler-Nichols, and change rules. So talking about robust response time is automatically tunes the PID parameters which is to balance the speed, response, and robustness. When the second method of tuning is Ziegler-Nichols, is very popular in industrial and real-time applications. So it's focusing on the very popular tuning rules. And another method of tuning, we use Chain-Ronson-Roswicks, which is derived from the original Ziegler-Nichols, but the intention is to obtaining the quickest response overshoots. So as we can see, the control law of PID as in equation 6. So this is the tuning rules that apply in PI controller and PID controller. So for this analysis and result, we use both for ROUC. Okay, so table 2 also show a full controller, which is proportional gain, integral gain, and derivative gain, apply with Ziegler-Nichols tuning rules. Another method, we use Chain-Ronson-Roswicks, also have the same analysis for both PI controller and PID controller. And this is the electromagnetic schematic design for ROUC. So to ensure the electropneumatic ballast tank system working properly, so we apply PID control to ensure that functionality of ballast working as expectation during movement on seabed, movement of the ROUC in seabed. Okay, so now we are in the results and discussions. After we apply all the methods, we compare all the results, okay, we can have a parameter which is applied in control system. We are focused on overshoots, percentage of overshoots, rise time, setting time. Okay, based on this is the result that we receive. We can see only uncompensated ROC not achieve the best performance of control system, especially on the overshoots, rise time, settling time. However, we need to see the three methods that apply: robust time, Ziegler-Nichols, and also Chain-Ronson-Roswicks. As we know, the Chain-Ronson-Roswicks to be as a quicker response time, all the application in PI controller and also PID controller show that there is the best in the settling time. And this is the results on the PI control transient response for ROC under different tuning method, except for uncompensated. Okay, we can see that the overshoots from robust response time is better compared to other two methods. And this is one-way ANOVA, which is the analysis part we apply as a single analysis of variance. We can see that C1 is uncompensated system, C2 is the robust response time, C3 is Ziegler-Nichols, and C4 is Chain-Ronson-Roswicks. So this is the comparison among of the four of the three methods, including uncompensated, which is without any controller. So this is based on the PI controller. And this is the results on the transient response for the three different tuning methods, including uncompensated. You can see again the PID also. You can see that robust response time achieve the best overshoots, but however the Chain-Ronson-Roswicks is good in terms of settling time. And this is result on the analysis of variance. So based on the option on the analysis of variant, single one-way analysis variant, that we have a best is C2, which is referred to response time. So on the analysis of variant, we can conclude that the robust response time have the good values in terms of analysis of variance. So this is the prototype of ROUC, and this is the testing and commissioning work that was done by my students in our Unicare Robotic Industrial Automation Center. So they need to testing. So this is the test bed. It's not the real one, but we apply to this test bed, okay, to see some leaking on the ROUC. Okay, so then we successfully merge the ROUC inside the water, and then we have the results based what we received just now. Okay, using PID control to ensure all the electropneumatic valve is functioned properly when the testing time. So as a conclusions, the transient response performance and one-way ANOVA show that the electropneumatic ballast system of ROUC is successful applied. Then we can conclude that the best tuning method is robust response time, which has the best transient performance based on the percentage overshoot. However, tuning method need to improve in order to have a good rise time and settling time. Okay, thank you. That's all for my presentation.